Welcome back, everyone. The first thing I want to mention is our second exam is going to be coming up a week from Friday. It will be the same format, and I expect to see a big improvement in it. As I've mentioned before, you cannot just sit back here in class without taking notes while you're watching, and you cannot sit and watch the video without taking notes. You're supposed to be spending at least 2 hours for each class during the week outside of class and outside of watching the video, which means you should be spending a minimum of 6 hours a week extra. Going over the video, going over your notes, studying, looking in the book, reading, whatever. Right now, we're going to be finishing up the first main idea in this section. Actually, we have finished it up. And that was the conservation of energy. And it was the realization that heat is a form of energy. We'll talk about what it is here very shortly. But heat is a form of energy. And that means that when you include heat in the list of all the different energy forms I had up there, there's kinetic energy, there's all different kinds of potential energy, there's radiant energy, light, and then there is heat. When you take all of those energy forms, you find that you cannot create or destroy energy. All you can do is change its form, which is profound because it means that the total energy here today is the same as it was 3 billion years ago. It's just been redistributed. Okay? So this led to the first law of thermodynamics, which was the conservation of energy. This has incredible consequences in everyday life because it means that since we cannot create or destroy energy, all we can do is change its form. And since we personally and as a society need energy, there are companies out there that are willing to find the energy and sell it to us. And we're talking about trillion-dollar industries. Trillion-dollar natural gas, oil, coal. We're talking about planet-wide trillions of dollars. And the consequences of that, of burning fossil fuels over the last 200 years, is that we are raising the overall temperature of the planet and we have global warming. And the difficulty that I see is there is zero attempt to control our usage of energy. Now you'll see false prophecies like hydrogen technology and electrical vehicles. I talked about these too, just to back up a little bit. Electric vehicles, pollution-free, right? Rubbish. You have to get the electricity to charge the vehicles, and that comes from burning coal, oil, natural gas at a power plant or windmills, hydroelectric dams, and so forth. You still have to use electricity to charge them, and that electricity has to come from someplace. What you're doing is moving the pollution from your location to wherever the power plant is. It's not a solution. You'll also see in the movie Angels and Demons, they talk about antimatter. Well, I'm an antimatter specialist. That's my area. And yes, if you had antimatter, you could use it to generate energy, but you have to create the antimatter. You would have to run a power station years to produce even a gram of antimatter. It's not a source of energy, it's just a different form. So there are incredible political consequences of this conservation of energy and environmental consequences as well. Anything we do in excess will change the climate. They'll talk about extracting energy from waves. Everybody heard about that, using waves? You do that, you are going to cool the ocean. that energy ultimately came from sunlight. You're extracting energy from the ocean. Start doing it on a huge scale, which is what we always do, and you're going to alter possibly ocean situations, and that's going to cause problems too. The obvious solution is to use what we have more efficiently and to have fewer people. There are too many people on the planet. Yes, 1,000 years ago it was good to go forth and have babies. Nowadays we are at the point where this planet cannot support the number of people. It's like we ourselves are a virus on the planet, destroying the planet. And we have to cut back on the number of people. That will cut back on the energy uses. But why don't we do that? Katie, why don't we do that? Why don't we cut back on the energy usage? It's real simple. Bryce? We can't afford to?
Won't afford to?
The problem is they don't want us to, because then they won't make money. They don't want us to decrease the population. They don't want us to use the energy more efficiently. They want to sell us energy. They want to make money. All right? Now, the question is, if heat is a form of energy, what kind of energy is it? Is it some kind of potential energy, or is it kinetic energy, or is it an absolutely new form, or what in the world is heat? And what we're going to answer now are two things. What kind of energy heat is, and also we're going to come up with a new temperature scale. The secret to what heat is comes from James Joule's experiment. Joule found that stirring the water makes it warmer. All right? That stirring the water warms it. You can do this now. You could take an egg beater and put it into an insulated container of water and beat the heck out of it, and the temperature will go up. One of the things you will find is it takes a tremendous amount of work to raise the temperature of something. Notice how hard you have to rub your hands to get them to go up in temperature. It takes a lot of work for a little bit of heat. That also means a small amount of heat can produce a lot of work if you know how to do it, which is where we're going to be going with this. If heat is energy, then heat can do work. And that's what we're taking a look at. But first, if we understand what it is, stirring the water warms it. Now, we do know, and you could argue that this is a seventh or eighth idea or a ninth idea, that the world is made up of atoms and molecules. And one of the most famous experiments that tells us that is called Brownian motion. And what is done in this experiment is that if you take some dust particles, and you notice this in the spring when the sun comes in through the window, you will see how your house needs cleaned because you see all that dust floating around. So if you light the air the correct way, it's very easy to see all the dust in it. Well, you have to do that, but you have to do it in a windless environment. You have to do it in a controlled space where there's no wind or anything. And then you have to look at the dust particles through a microscope. And what you'll discover is that under the microscope, because the dust particles are influenced by gravity, they will be falling down, but then suddenly, it will change direction and then start up. Well, if that's happening, there has to be something changing its velocity. It has to be hitting something. And what you're actually seeing in that case is the molecules of the air striking the piece of dust and changing its trajectory. So evidently, the molecules in the air are moving in a constant, random fashion. And this is the best way to imagine it. Now in here I have what are called superballs. And these are so hard that they will bounce almost all the way up when you bounce one. And if I agitate them, you can see that they're hitting the walls of the container, and they're also hitting each other, and it is a very helter-skelter arrangement. Some of them are going very fast, and some of them are going very slow. But there's kinetic energy in there. Well, these superballs are made of molecules. And because of that, the energy that they have can go inside the ball and turn into heat. But when you have true molecules, when molecules collide, they must collide elastically because there's no place inside for the energy to go. So what is happening is all of the molecules of the air in this room are doing this. They're hitting your body, they're hitting the table, they're hitting themselves. But unlike what we see here, notice if I stop shaking it, these ones stop. This does not happen with the molecules here in the air because they are elastic collisions. No energy is lost when they collide with each other. They can exchange energy. And when they hit the walls, all of the molecules in the wall are undergoing this constant vibrational motion. So when they collide with the walls, they don't lose energy either. And the floor and the ceiling. So out here in this room is a tremendous amount of this random, disordered, internal molecular energy. That is what heat is. It's internal, it's random, that's very important. You see, if I take this and I move this sideways, like if I shot it from a gun, you could do that. They got guns that'll shoot pumpkins, right? There's a pumpkin shooting contest right now somewhere. You can shoot this and then all of the balls would be going at the same speed in the same direction at the same time. That's very organized. That's not the same as this, where it's all completely disorganized. It's random. The randomness is a very important aspect of what we call thermal energy. So what kind of energy is heat? It is random, disordered heat, which we also call thermal energy. Some people argue, I don't worry about it, that heat is a flow of thermal energy, but heat is random and disordered internal energy. The random and disordered part of it is very important. Also, that it's internal. This energy is constantly being moved around, but in this room, for instance, none of that random, disordered kinetic energy turns out to be lost. So this is called the kinetic molecular theory of heat. And it is correct. All right. The kinetic molecular theory of heat treats heat as random, disordered, internal energy. And it's everywhere. It's in the walls, it's in you, it's in the air here. And because it is energy, and energy is the ability to do work, it could be used to operate a train, move a car, pump water, saw wood, or do anything that any of the potential or kinetic energies could do. And we're going to see how you do that. Now, if these molecules are beating around like this, like that, well, they exert a force on the walls of the container. And in fact, if you make a careful measurement, you will find that the molecules in this room right now, if you look at the force that they exert when they beat on a square inch of surface, it's about 15 pounds. All right? So that means if you have a sheet of paper that's 10 inches long and 1 inch wide, there's 15 pounds per square inch. There's 150 pounds on just one little strip. There's probably about 900 pounds or half a ton of force on this sheet of paper. Now, I see skepticism. Good. So what would happen if I put a ton of force on this side of the paper, or if I put a ton of force on the outside of this bottle? What would that do to it? If I put this in a press and stuck a ton of force on it, what would happen?
Break.
It'd break. So why isn't it breaking?
Is this distributed evenly?
Go ahead.
It's distributed evenly?
Part of it. Okay, what would happen if I took a gas can? Not a plastic one, one of the metal ones. Well, you can use a plastic one. So all the air molecules are beating around the, it's an empty gas can. All the molecules are pushing on the outside. And you look at that, man, there's probably a ton of force on that taking over all of the surfaces. So how come it isn't just absolutely crushed down?
Because there's more pushing the other way?
Yes! There's air inside. Is it Kate? There's air inside. What would happen to that gas can if I sucked the air out of the inside? It would crush. And in fact, if you ever go up in the mountains with the gas can that's got almost empty, when you come back down, it could crush. It could crush because the pressure changes. This is called pressure. So these molecules bouncing around exert a force. There are tons of force on the desktop. But there's a ton of force underneath the desktop too. And there's a ton of force, well, not a ton, but huge amount of force on your head, but inside your brain cavity, it's pushing back. If you were to take the brain out of a cadaver and then suck the air out of the head would be crushed. Okay? The head would be crushed. So it's the fact that the forces are balanced. And by the way, they're bouncing in all directions, so are they pushing against the board? Yes, there's 15 pounds of force for every little square inch of the board. So how many of those are there on the board?
A lot.
A lot. There's a huge force on this board, but it's not crushed because behind it, the air gets behind it and pushes the other way. It pushes in all directions. See, it's disorganized. If you take two people and say, go out there and move that crate out there, if they push against each other, nothing happens. What you have to do is have the two of them push from the same side. So what would happen if I had a board like this, mounted it in a place, and sucked the air out from the back of the board? The board would get blown out. This is what happens in storms. A tornado can come by and the pressure can be lower on one side of a house. It's higher inside, the air doesn't have any time to get out, and so poof, the whole house just blows up. It can and has happened. All right? So heat is this random, disordered internal energy, and this finally leads to an understanding of what temperature actually is. Finally, we're going to find out something better than just saying a temperature difference causes heat to flow. That's true. But it doesn't tell us what temperature is. Now you're going to find out what temperature actually is. It comes from experiments that were done in the 1800s. If you take something like a balloon, and a balloon has the property that if you blow some air into it, it tends to keep the pressure constant. that if you, does anybody know if you go buy a balloon from Walgreens or Rite Aid, you know, one of those helium metal balloons, what'll happen to it if you stick it in the freezer? It goes wimp. It wimps out. It shrinks. It's not tight anymore. But then you take it back out, and it comes back up. So if this is the volume of an ideal gas, now an ideal gas is any gas like helium, hydrogen, nitrogen, just about any of them at normal room temperature. These effects don't really become apparent until you get things really cold. And so they were studying gases, and they were studying the effects of temperature. And on here we have the temperature in degrees C, and here we have the space occupied by the gas. Okay? Volume is the space it occupies. You put it into a container that can change size. The easiest way to imagine this, actually, and we'll explain it in a minute, okay? But here's what we find, is that if you consider this, let's do it here, that if you change the temperature and you measure the volume, this is 100 degrees C, boiling point of water. You can go higher than that too. If you do an experiment at temperatures, you know, up to maybe a couple hundred degrees, boiling point of water and above, and you plot it, what you get are a bunch of points. You see that it occupies less and less space as the temperature goes down. And as they were learning how to make refrigerators that could cool things colder and colder and colder, they found that in most cases, the gas would eventually liquefy. It would become a liquid. It has, most normal gases that we encounter have, they boil, and if they freeze and condense at really cold temperatures, like 200 degrees below zero or something like that. But they will turn into a gas, or a liquid. Yes?
Is that because the speed of the molecules is slowing down?
We're getting to it.
Oh, sorry.
Yes. The question is, it's because the speed of the molecules is slowing down. The answer is yes. But let's not worry about the molecular nature of it yet. But essentially what happens is they start to link up, and then they liquefy. Get them cold enough, they solidify. They become a solid. You can have solid oxygen. You can have a brick of oxygen. It's got to be pretty damn cold, but you could have a brick of oxygen. And I'd love to do that. Okay. All right? Now, once they do that, once it liquefies or solidifies, well, it doesn't shrink up nearly as much anymore, right? It doesn't shrink down. It does a little bit, but not like it did when it was a gas. So you say, okay, this is what it was doing when I made my measurements. It follows, am I that boring? No, it follows a straight line. And so now you say, what if I could keep cooling it, and if it didn't solidify or liquefy, if it stayed a gas and I continued to cool it, in other words, if it behaved ideally, this means it would never solidify. What I predict is that there is a temperature right here which it would not have any volume whatsoever. The space that it occupied would be zero. Now, of course, that can't really happen. But if it behaved ideally, if it didn't solidify or liquefy, and helium is almost perfect. Helium, this will go all the way down to like right there, and then it finally liquefies. Well, you do this experiment, and you find that that temperature is roughly negative 459 degrees Fahrenheit. Imagine 459 degrees below zero Fahrenheit. It takes special refrigeration to reach us, but we have that. We have that. You say, well, okay, that can't really happen. So that can't really happen, and so this is not really of any other interest. But here is what's weird. If you do this with experiment with a different apparatus, a different size container, you get the same temperature again. If you do it with a different gas, the graph might look like this. So the data might look like that. But if you extrapolate backwards down in temperature, no matter how you do the experiment, this temperature keeps coming out regardless of which gas you used and the apparatus you used. You get that the volume would go to 0 at this temperature. Clearly, that temperature means something. It means something. Now, if you want to visualize this, imagine that I make a thermometer by taking a tube, a glass tube, and I put a plunger in it with a weight on it. So there's a weight on the plunger, and the plunger has to be perfectly sealed, and it has to be able to move up and down with no resistance. That's not easy to do. And we put some gas in here, so what we know is going on is that gas is doing this. But as we cool it down, evidently the molecules slow down. They don't go as violently. What we have here is, in an ideal gas, we have internal kinetic energy. But it's not organized kinetic energy, it's disorganized kinetic energy. So as we cool it, these slow down. Now they're hitting this plunger. They're hitting that plunger and bouncing against that plunger, and that tends to push it up. So what will happen is, if we leave it alone, the plunger will move down until the number of molecules hitting it is such that the downward force of gravity is balanced by the upward force of the molecules, and it will just sit there. If I cool it, the molecules will slow down. Well, that means they don't hit this as hard, so it's not balanced anymore, so it moves down until these get packed a little more, and so even though they're not hitting as hard, more of them are hitting, and eventually it will equalize again. So at any temperature, there's an equilibrium position of this, and we can put a scale on here. And the position of the plunger indicates the temperature. This is a gas thermometer. Evidently, as you slow the molecules down, this will keep moving down until essentially it reaches the bottom and the molecules don't occupy any space whatsoever. This is the prediction of all experiments. They all predict this same particular temperature, which we now call 0 degrees Kelvin, or 0 Kelvin, or absolute zero. Absolute zero. What is going on here? We are seeing the amazing thing that there is a lowest temperature. You cannot cool something forever and get it colder and colder and colder. This is the coldest temperature. In fact, we're going to see that it is the cold temperature limit. it turns out you can't actually reach that temperature. What we find in the laboratory is that when we try to cool things, as we get near this temperature, it becomes more and more difficult to lower the temperature further. And despite all of our efforts, we can't actually reach this temperature. It is a limit. It's kind of like I say, walk over there to the wall and take, each step is half of the distance remaining. So your first step is huge. Then your next step is half of that, your next step is half of that, half of that. Will you ever get to the wall? If I only say you're only allowed to take a step half the distance remaining, will you ever get to the wall? No, because half of the distance will always be remaining. You can never get there. You can get as close as you want. But if I say your steps must always be such that you only cover half the remaining distance, you will never get there. But if you want to get within a billionth of an inch of it, you can do that. But then you can get to a half a billionth of an inch, a quarter of a billionth of an inch, an eighth. You'll never get there. That's why it is a limit. And this is what we call absolute zero. It's also negative 273 degrees C and negative 459 degrees Fahrenheit. So what we have now is a new temperature scale. This business of having to say negative temperatures is a pain. Remember, the metric scale is based on the melting point of water and the boiling point of water. This one is based on people being originally about 100 degrees, and the coldest temperature you can get with a salt solution. Those are arbitrary choices of the zero of temperature. We just choose it. But in this case, if this is the cold temperature limit, you cannot have a negative absolute temperature. Yes?
This might be a really dumb question, but when the gas thermometer, when the weight is going down and there's less space for the molecules to move around, how does the pressure not increase and increasing the speed of the molecules?
What happens is the speed, okay, I'm going to answer that. I mentioned the kinetic molecular theory, right? It's related to this. What this states, whoops, I can spell what this specifically says is in a perfect gas, okay? So it means you're not near the liquefaction point, you're further up. The average kinetic energy per molecule of an ideal gas. So an ideal gas is, again, we have this thoroughly random motion. Some are going fast, some are going slow. So they have different kinetic energies. But you can find an average. You can find an average. The average kinetic energy per molecule of an ideal gas is directly proportional to the absolute temperature. This is called the absolute temperature scale. So what happens here, as you cool this down, these go slower. And given that this is at some temperature, regardless of where the plunger is, if it's all stabilized and at some temperature, what happens is if you slow them down because you cool it, they can't push up like they're supposed to because they're going slower, right? So this moves down, but as it moves down, they get more compacted and they hit it more often. That makes up for the fact that they're going slower. So eventually a point is reached where they push up with the same weight as gravity pulling down, and it stabilizes. So as you lower the temperature, it moves itself down. If you've got it all the way, so look at this. What if the absolute zero temperature is absolute zero? What's the average kinetic energy of the molecules? What's the average kinetic energy of the molecules right there? Zero. Now this is not totally accurate because these aren't molecules, but you can see that as the temperature goes down, they eventually reach a point where they wouldn't be moving at all. And that means this thing would be all the way down at the bottom. See? And so when this is at the bottom, that's absolute zero. Can it go below the bottom? No. You cannot have negative absolute temperatures. Not possible. This is a temperature scale, and let's list it here. If I were to put these three temperature scales here now, and just list the temperatures of common things, so these are the things you have to know. So here's the absolute temperature. That's also the Kelvin temperature. This is also called the absolute temperature or the Kelvin temperature because a man named Lord Kelvin worked on this, or the thermodynamic scale, the thermodynamic temperature, or the absolute temperature. They're all the same. And here we have absolute zero. And then over here we have the metric scale. And then we have the English scale, our scale. The English scale, by the way, this is called the Celsius. And this is the Fahrenheit for the man who established it. So absolute zero is, guess what? It's absolute zero. Okay, it's zero. This is negative 273 degrees C, negative 459 degrees C. It's incredibly cold. It actually turns out that even outer space is not at absolute zero. Outer space is about 3 degrees above absolute zero. The only place you'll find colder than 3 degrees Kelvin is if you go to the moon and go under a crater, under a rock or something, then it might be colder there. Okay? Then there is ice melts. And that is at 273 Kelvin, 0 degrees C, or 32 degrees Fahrenheit. Water boil. There's one other room temperature. Room temperature is 293 degrees Kelvin. It's about 20 degrees C. That's 68 degrees Fahrenheit. You need to know these temperatures. There's only one way to learn that, and that's just to memorize them. You need to, they will be on the exam. There will be a question on the exam about these scales. Water boils, sea level. That's at 373 degrees Kelvin. that's at 100 degrees C, or 212 degrees Fahrenheit, and there is no upper limit. You go into the interior of the sun, it can be millions of degrees Kelvin, and inside other places in the universe it can be even hotter than that. The key takeaway from this is, remember we said that the absolute temperature is about this random, disordered, internal kinetic energy. Don't call it kinetic energy. Don't call it that. Kinetic energy is when everybody is organized. Okay? Everybody's going the same direction, same speed. It's disorganized kinetic energy. That's called heat. Okay? The point is that even when it's 32 degrees Fahrenheit outside, or 0 degrees C, it is 273 degrees above absolute zero. As far as absolute zero is concerned, that is boiling hot. Compared to the coldest temperature possible, even when we as humans think it's cold outside, this is incredibly hot. Notice there's only 100 degrees between ice melting and water boiling. We're talking about almost 300 degrees down there. Even on the coldest winter day, the air outside holds a tremendous amount of heat. The air outside is full of heat. And heat's energy. Energy means you can do work. If we could find a way, think about this. Think about this. This is my dream. And it's what we call a pipe dream. Never going to happen. I pay to heat my house. When they come by and put oil in my tanks, I'm writing a check. One check for about $900. Even when it was higher, when the oil prices were higher, I'd shell out $1,000 one day. Boom. Now that might provide my heat all the way until, say, February. Then I'd have to shell out some more. Remember I said it was big business? Oh yeah. Oh yeah. If I could buy a machine that I could put outside my house on a little concrete pad that could take the energy in the air outside, even on a winter day, and use it to drive a generator, because it's supposed to be able to do work, right? And generate electricity, I could run my house completely on electricity, including an electric heating system. And if I needed more, but if one of these little things couldn't generate enough electricity, well, I'll put a few more of them out in the backyard. And they'll just suck the heat energy out of the outside air, turn it into electricity, and I'll run my house, including an electric heating system on it, and never have to pay the electric company, and never have to pay the oil company, and never have to pay the gas company again. Wouldn't that be great? As we're going to see, you can't do it. It's not possible. We are going to see where we're going to go is, if heat is everywhere, and everywhere is well above the coldest temperature possible, that means heat's all over the place, outside, in the ground, in my house, in the air here. If I could find a way to convert that heat into useful energy, that's called a heat engine. You want to start reading. Look up heat engine in the book in the back. We're going to look at heat engines. The first and most important was the steam engine. What we are going to see is that when you try to convert heat into useful work, you can do that. That's what a steam engine does. You burn the coal. That's what your automobile engine does. What do you do with the gas in your car? What does a spark plug do to the gas? Burns it. You take the chemical energy, you immediately turn it into heat. And then the engine in the car turns that into whatever. Your car could run a generator to even run your house, okay? But what we're going to find is that when you try and convert the heat into useful energy, another law in nature comes in which says you cannot convert all of it back. You can take a gallon of gasoline and you can convert it into heat. You just set it on fire. Okay? Just set it on. Throw it outside in the backyard. Please don't burn on the forest. Light it, and all the chemical energy gets turned into heat. Well, what you want to do is take that heat and then turn it into electricity. What we're going to see is you cannot ever convert all of the heat back into one of the other energy forms. That's going to be the second law of thermodynamics. Let's stop right there.